Hi, my name is Ruth Abata. The research paper I'm going to present about is model-based steganography with Precover. Uh, this research paper discusses on a theory-driven approach to model-based steganography, a method of hiding information which within digital image in a way that's more secure than traditional approaches. This research builds on previous historic techniques by using a formal mathematical model based on multivariate Gaussian noise to optimize the embedding process. Let's dive in. First, let's define steganography. It's a technique used to conceal messages within cover objects, such as digital images, videos, audio files. Unlike encryption, which hides the context of the message, steganography hides the very existence of the message itself. The challenge here is security. How do we embed data without detection? Side-informed steganography is a technique that enhances both security and efficiency when embedding secret data into images. Rather than randomly altering pixels to store information like traditional steganography, this method strategically selects pixel value that minimize distortion. This makes the hidden message much harder to detect. In simpler terms, it blends the change more naturally into the image, making it less likely that detection tools or even advanced forensic techniques will notice anything unusual. Why is it important? Because traditional steganography, like LST embedding, often leaves behind statistical trace that makes detection easier. Side-informed steganography avoids this problem by using knowledge of the original image structure to embed information more naturally. There are two advantages of side-informed steganography. It reduces detectability. Because the embedding process considers the natural variation of the image, it's much harder for detection algorithms to identify hidden data. It improves embedding efficiency. This means more information can be stored without increase the risk of detection. So in short, this technique makes steganography safer and more effective. Now let's talk about the other side of steganography, which is steganalysis. If steganography is the act of hiding information, then steganalysis is the process of finding it. It works by analyzing images to detect irregularity that suggests something has been hidden. This is especially useful for cybersecurity, law enforcement, and forensic investigations. One way steganalisis works is by using statistical analysis and machine learning models to compare an image to what a normal, unaltered image should look like. If certain pattern appears true or artificial, the image is flagged as potentially containing hidden data. Now let's see this image. Look at image A. This is an original unaltered image. It's just a normal picture with no hidden data. Now let's look at image B. This is a different cover image used for embedded comparison. Now let's look at image C. This one has hidden image embedded using side-informed steganography. At first glance, Does anything seem different between A and C? Exactly. They look nearly identical. That's the power of side-informed steganography. It ensures that the image doesn't show obvious sign of tampering. Now let's look at image D. This is the result of steganalisis technique applied to the image. Here you can see distortions and patterns that reveal the presence of hidden data. Why does this happen? Because even though side-informed steganography is effective, advanced detection techniques can still identify hidden data by looking at pixel-level anomalies that aren't obvious to the human eye. So, why does all of this matter? Well, steganography is used in various real-world applications, like cybersecurity, protecting sensitive information by embedding it in digital media, forensic investigations. Law enforcement agencies use tag analysis to uncover hidden messages in criminal investigations. And covert communication. Some attackers use steganography to hide malicious code inside images, making cybersecurity professionals rely on stag analysis to detect these threats. Existing side-informed steganography techniques are largely heuristic. Heuristic steganography is a technique that relies on heuristic optimization, essentially trial and error methods, to detect where and how to embed secret data in an image. It's an intuitive thought, meaning it's not based on strict mathematical theory, but rather on what seems to work best at the time. This makes it flexible, but also includes serious weaknesses. There are two major issues with heuristic methods, and that's why researchers needed to develop something better. Number one, based on intuition rather than formal theory. Traditionally, heuristic methods rely on best guesses rather than proven cryptographic models. This makes them vulnerable because they lack a solid mathematical foundation, meaning their security cannot be formally verified. Think of it like building a lock for a safe based on what seems stronger. Rather than testing engineering principles, if any attacker figures out the pattern, they can break it easily. And the second one, it's inconsistent security. Since heuristic steganography doesn't follow a strict, predictable model, its security level can vary from image to image. Some images might conceal data well, while others may expose it without the user realization. This makes it unreliable for high-stake applications like cybersecurity, government intelligence, or secure communication. Can you guess which one of the cat in the box image original and which one has a hidden message? Well, the left one is the original image and the right one has hidden message inside it. The model-based approach. Unlike heuristic methods, which rely on rules of thumb, this approach is grounded in statistical theory. The key idea here is to model the acquisition noise. The random variation introduced when capturing an image as a multivariate Gaussian distribution. This allows us to mathematically describe how the noise affects the image. By using this model, the authors can design an embedded rule that minimizes the KL divergence between the cover and stego image, making them statistically similar and hard to detect. Let's break this down. The Gaussian distribution, also known as the normal distribution, is a bell-shaped curve that describes how data is distributed around a mean value. In this context, the Gaussian distribution models the acquisition noise at each peak. So let's look at this equation. X is the noisy pixel value, T is the true pixel value, and omega square is the variance of the noise. So why Gaussian? Because many natural process includes linear noise. Following this distribution, it's a well understood and mathematically tractable model. Now let's talk about KL divergence or Kullback-Leibler divergence. This is a measure of how one probability distribution differs from another. In steganography, we want the stego image to be statistically indistinguishable from the cover image. The KL divergence quantifies this difference. By minimizing the KL divergence, the author ensures that the stego image closely resembles the cover image in terms of its statistical property. This makes it harder for an attacker to detect the hidden message. So why is it important? Traditionally, steganographic methods often rely on heuristics, which can be less secure. By using a model-based approach, the author provides a stronger theoretical foundation for designing secure steganographic systems. This approach is particularly effective because it adapts to the acquisition noise and content complexity of the image. It's not just about hiding data. It's about hiding data in a way that's statistically unpredictable. Now let's dive into the modulation factor using in the embedded process. In steganography, the goal is to hide data in a way that minimizes detectability. One way to achieve this is by modulating the embedded cost, essentially deciding how much it costs to change a pixel value based on how detectable that change might be. Previous methods used heuristic approach, modulating the embedded cost by a factor of 1 minus 2e, where e is the rounding error. This was based on the idea that pixels with larger rounding errors are less likely to be detected if changed. However, this paper argues that this heuristic is not optimal. Instead, the author proposes a more accurate statistical model that uses a modulation factor of 1 minus 2e the power of 2. Let's break this down. The modulation factor determines how much we adjust the embedding cost based on the rounding error e. In previous methods, the factor 1 minus 2e was used. This means that if rounding error e is close to 0.5, the cost of changing the pixel is reduced significantly, making it more likely to be changed. However, this approach is heuristic. It's based on intuition rather than solely theoretical foundation. The author of this paper argues that a more accurate model should be 1 minus 2e the power of 2 instead. Why? Because squaring the factor makes the modulation more sensitive to the rounding error, leading to a more secure embedded process. Now let's look at the maths behind it. The modulation factor 1 minus 2e the power of 2 is derived from the Fisher information, which measures how much information a random variance carries about a parameter. In this case, the Fisher information tells us how much the embedded process affects the statistical property of the image. By using 1 minus 2e the power of 2, The authors ensure that the embedding process minimizes the detectability of change. To put it simply, 1 minus 2e to the power of 2 is a more accurate way to modulate the embedding cost because it better reflects the statistical impact of changing a pixel value. Let's compare the two approaches. In the previous method, the modulation factor 1 minus 2e was used. This factor linearly decreases as the rounding error e increases. In contrast, the new approach uses 1 minus 2e to the power of 2, which decreases quadratically. This means that for larger rounding errors, the cost of changing a pixel is reduced even more, making the embedding process less detectable. This is a significant improvement because it aligns the embedding process more closely with the statistical property of the image, making it harder for an attacker to detect the hidden data. So what does this mean in practice? By using 1 minus 2e to the power of 2 instead of 1 minus 2e, the author achieved a more secure embedding process. This is particularly important for high-quality image and large payloads, where even small change can be detected by sophisticated steganography tools. The improved modulation factor makes the stego image statistically closer to the cover image, reducing the risk of detection. To conclude, this research presents a significant shift in how we approach steganography by introducing a structured model-based method that improves security and reliability. Traditional heuristic techniques, while commonly used, are largely based on intuition rather than formal mathematical foundation. This lack of structure often results in inconsistency, making them vulnerable to detection. Heuristic methods may work well in certain cases, but they do not guarantee security under all conditions. This is a major concern, especially as tag analysis tool and detection technique continues to advance. By contrast, the model tech-based approach proposed in this research move away from those uncertainties, providing a more synthetic, mathematic, and theoretically sound framework for hiding information. A key innovation in this approach is the use of side information, specifically through the concept of a precover. Instead of embedding hidden message directly into an arbitrary cover medium, this method leverages additional information to guide the embedding process. This means that rather than making unpredictable modifications that may introduce statistical irregularity, the embedding process follows a well-structured defined structure. By incorporating this follow additional layer of control, the model-based approach ensures that the modified media remains statistically consistent with its original form, reducing the likelihood of detection. This is an important step toward more robust steganography techniques that can withstand increasingly sophisticated attacks. One of the most important aspects of this research is the minimization of KL divergence, which measures the difference between the statistical distribution of the original cover, or the stego object. The goal of effective steganography is to make the stego object indistinguishable from the original, preventing adversary from identifying modification. When KL divergence is high, the change introduced by the embedding process becomes detectable, increasing the risk of exposure. By focusing on minimization, this divergence, the proposed approach ensures that the stego object remain as natural as possible, significantly enhancing security. In practical terms, this means that message can be hidden more effectively, even against advanced tag analysis tools that rely on statistical detection methods. Another critical importance comes from the modulation of feature information, a measure of how much information can be extracted about an unknown variable. In the context of steganography, this concept plays a crucial role in balancing security and efficiency. If too much information about the embedded message is available, the stego object becomes easier to detect. Conversely, if the information is too limited, it can affect the quality and usability of the media. This research introduced methods for carefully modulating feature information to optimize this balance, ensuring that hidden messages remain undetectable while maintaining an efficient embedded process. This represents a major advancement over traditional heuristic methods, which often fail to account for such trade-offs. Beyond these technical improvements, the significance of this research extends to a broader field of information security. As digital communication continues to evolve, so do the threats posed by adversaries attempt to intercept and detect hidden messages. Existing steganographic technique must continuously adapt to counteract emerging detection methods. By moving beyond heuristic and approach and adapting mathematically rigorous models, this research provides a foundation for the next generation of steganographic systems. It highlights the importance of combining theoretical principles with practical application to enhance security in real-world scenarios. In summary, this work demonstrates that relying on intuition alone is no longer sufficient for effective steganography. A more structured approach grounded in information theory and statistical modeling is needed to ensure long-term security. The introduction of side information to precovers, the minimization of KL divergence, and the careful modulation of feature information all contribute to a more secure and reliable steganography frameworks. This improvement marks a step forward in the field, paving the way for future research into even more advanced techniques. As steg analysis methods continue to evolve, it is crucial to remain ahead by developing security solutions that are not effective today but also resilient against future threats. By continuing to refine, expand upon these ideas, we can push the boundaries of what is possible in secure information, ensuring that the privacy remains a fundamental right in the digital era. While the model-based approach shows significant improvement, it does have some limitations that are important to consider. Number one is computational complexity. The model-based approach is more computationally intensive than heuristic method. This means it requires more processing power and time, which could be a drawback in time-sensitive applications. And number two, its sensitivity to parameter estimation. The method relies on accurate estimation of noise variance and other parameters. Poor parameter estimation can reduce the effectiveness of the approach, making it less robust in some cases. This research also shows significant promise for future work in the temporary embedded and more general side information scenarios. Any questions? Remember, the best way to hide something is to make it blend in perfectly. Thank you.